Thank you so much for that heartfelt introduction. I'm really very, very happy to be here. It's a long road to be in this conference. I met Fernando, we were just remembering, in 2012 at a reproducibility workshop. And he gave a talk about IPython. And I just knew immediately this is what I wanted to use in my class starting in a couple of weeks. And so he installed it in my laptop, and I fired up and went on a long-haul flight, and started to learn how to use it right away. That was 2012, and I published my first course with, back then, IPython notebooks in 2013. And I had the opportunity to give a keynote in 2014 at SciPy, the SciPy conference, where I boldly claimed that Jupyter was going to be the killer app for education. And here we are. So I'm very happy to now address a kind of a different topic, thinking about the issue of reproducibility. Of course, you must have seen all of I'm not going to bore you with a slide with all of the screenshots of the covers of topics, articles of about reproducibility, or the crisis in reproducibility in science that have appeared in Time and The Economist and on the New York Times and etc. But I want to tell you about the beginning of this story. This professor that looks like Santa Claus is actually an emeritus professor at Stanford in geophysics, and he pioneered the use of computers for the processing and filtering of seismic exploration data. From 1991, that's a long time ago, he required all of the theses of his graduate students to conform to the standard of reproducibility, which meant that the thesis of the students should be reproducible programmatically by just one single command. All of the figures, all of the scripts, all of the analysis should be possible to be completely reproduced by a single command. Now, I guess if you're doing simple analysis, this might be possible in short time, but if you're doing HPC simulations, that is quite another story. But anyway, this is the beginning of the reproducibility movement. And this group in particular at Stanford developed their standards of reproducibility with standard commands, a filing system, a way to process and test their software for reuse. And I would say that to this day, computational researchers are still trying to measure up to Claerbout's standards. This idea that you can leave a finished work in a state where coworkers can actually reproduce the complete calculation and workflow with a single command. And so this is the beginning. Let me share with you the definition of reproducibility that we use, and we have adapted from a publication that appeared already almost 10 years later by the group of Claerbout. And this definition is that authors should simply provide all the necessary data and all of the computer codes to run the analysis again, recreating the results. Now, believe it or not, this is still somewhat controversial in some fields. This is about the first publication. So the group of Claerbout was the first to use reproducible research as a phrase, and this is the first publication where they share this idea. We have adopted this definition, and we, indeed, in my group, share all the data, all of the computer code that we use to generate any research results. A few years later, the community has developed this idea of a spectrum of reproducibility, because one thing is to share the computer codes and all the analysis, but quite another is to get to a point where somebody else can actually do a new study that confirms the findings, the scientific findings of a previous result. And this has been called, I'm sorry for the mic noise, this has been called replication. So reaching a full replication study means you collect new data again, you may use different methods perhaps, but you can confirm the finding. So there's a spectrum from the minimum standard of sharing the data and the code to this final idea of replication, all of which is to develop trust in the scientific process and the findings. And so this idea of replication, just to be on the same page, is to arrive at the same findings as another study, collecting new data, possibly with different methods. Of course, this is not always possible to do. For example, if you're doing an opportunistic epidemiological study, you might not be able to collect the data again because it happened at a given point in time. But on the other end of the spectrum, reproducible research is really only limited by the time and effort that we're willing to put in. Now, from the group of Claerbout comes this very interesting idea that I've been thinking about and I wanted to share with you. He writes in different places, different forms of this idea, that interactive programs, he says very harshly, are slavery unless they include the ability to arrive at any previous state by means of a script. So this is a big no to GUIs if you want to do reproducible research. I gave one talk where I to a group of computational scientists where I mentioned this, and there was big pushback from the audience. So that's an interesting idea. On the other hand, Jupyter is, of course, a set of open source tools for interactive exploratory computing. So from Fernando and Brian's post, The State of Jupyter, that appeared in the O'Reilly blog, they say that Project Jupyter aims to create this ecosystem of open source tools for interactive computation and data analysis, where the direct participation of humans in the computational loop, executing code, understanding a problem iteratively, is the primary consideration. So this is the idea. So, well, the idea of an interactive tool, in addition, being a tool that can help create this reproducible computation analysis is what I wanted to think about today with you. Because Jupyter is promoted as a solution for creating reproducible computation and analysis. Some see it as a means of putting into practice the idea of NUTH, of literate programming, where code is directly annotated by comprehensible documentation, the thinking process of the human in the loop. But some researchers object to this idea that Jupyter is good for reproducibility. They note so-called problems with the notebook because of the nonlinear nature of the interaction of code cells, unordered execution, and other problems with perhaps version control or not being able to integrate a workflow analysis. So there's been quite a bit of debate in some areas, in some communities, about whether the notebook is indeed a good tool for reproducible research. So what is this problem here? There seems to be a tension, a contradiction between interactivity and reproducibility. Indeed, interactive tools were seen by the pioneers of reproducible research as the complete antithesis of reproducibility. So what makes Jupyter different than, say, the dreaded spreadsheet? Why is Excel different than Jupyter? What is it about the interface, the tool? What is it about the design that it's different? Here is UC Berkeley Professor Philip Stark talking about Excel. I'll just let you read that. 2014, he gives a talk about using Excel for your analysis. So he wrote a blog post in 2014 titled "Science is Show Me, Not Trust Me." And he offers a checklist of points that you should follow for reproducibility. The first point in his checklist is, if you relied on Excel for your computations, fail. He explains that spreadsheets make it very hard to do reproducible research because it's hard to document and reconstruct what you clicked and what you didn't click, in what order you did it, and the user interface conflates input, output, code, presentation, and this makes testing and discovering bugs very difficult. So this is a problem. This is a problem of design. A problem of design standing in the way of reproducibility. The second point that he makes is that if you did not script your analysis, including all the data and all the cleaning and all the munging and all of the other steps, intermediate steps, then also that's a fail. Because so it doesn't mean that you cannot use interactive tools or point-and-click interaction in the intermediate steps, but it does mean that you need to, at one point, when you figured out what needs to be done, just put it all together in an automated process, script it out in a way that you can confirm that you can regenerate the whole process from scratch. And again, this is a design recommendation, a workflow design recommendation. Now, let me just make a parenthesis to make sure that we understand why we care about this problem of reproducibility. Why has it hit the New York Times and all of these major publications? Well, we care about computational reproducibility because we're using computing to create new knowledge. We're using it as an avenue for scientific discovery. It is so embedded in every single field of science today. It's really, computing is a form of learning and form of discovery. We're creating knowledge. And this is using computers as extensions of our mind. There's a whole field that analyzes representation modes and how some people call it material intelligence. For example, algebra, mathematics is material intelligence, something that we use as extension of our minds to make comprehensible the world. We make science with computers, and science demands reproducibility, so this is why we care about it. And science, there is a theory of learning called connectivism, and one of the leaders of this theory is Stephen Downes, a philosopher in Canada, with George Siemens. They were the first to do an open online course, Connectivist it was called, in 2008, way before the MOOC craze in 2012. And Stephen Downes says that science is a conversation. This is a simple statement, but it's rather deep. The idea that actually you do science by having a conversation with perhaps your body of knowledge, with other scientists, or a conversation between scientists and instruments and machines. This is the connectivist explanation of what really constitutes the process of doing science. What is a conversation? So here I take a few minutes to go in a little bit philosophical dive with you. This is, I guess, inspiration from the old field of cybernetics. And Paco Nathan is happy, probably in the room, that I'm mentioning cybernetics. And so what is a conversation? Participant A has a goal and contacts participant B, choosing a shared language. No shared language, no conversation, of course. Participant B needs to engage if the conversation is to continue, has a reaction, and the goal of that loop is to create a commitment, and that's where action happens. If those participants come to a commitment, then action can continue. The agreement is what we are looking after in a conversation. And when we agree in a community about a scientific discovery, this is a process that also is occurring. We can have conversations about goals, about means, and so on. In the interface, there could be some tool aiding that conversation. Now, how do we design conversations for reproducibility? And I only have a few minutes for this presentation, so I cannot really give you any more than the syllabus for this topic, thinking about it. And there is a very classic book by Herbert Simon, who was a Nobel Prize in Economy. He got the Turing Award, and multi-talented Professor Simon from Carnegie Mellon. And he says that design is concerned with how things should be, with devising artifacts for satisfying certain goals. Everyone designs who devises courses of action to change existing situations to make them better. Some inspiration we can find also in the classic works of user interface design. This book by Schneiderman is recommended. It's a standard going back to 1986 for the first edition. And he says that tools that succeed have to be comprehensible, predictable, and controllable. So an obscure tool does not satisfy this trio. Responsibility should guide design. Those who have authority and responsibility must have adequate levels of control. Who is the person who has responsibility in the process of science and in ensuring reproducibility? The humans. So we have this balance between the humans that need to be in control and this idea of automation. We must not relinquish the responsibility as humans and try to assign that to a tool. The idea of ensuring human control while increasing automation. So here is a quote of this pair of cyberneticians on 21st century design. Design has expanded from giving form to creating systems that support human interactions. So this is what should be our inspiration when thinking about how we make tools that are going to encourage reproducible research. These humans' interactions that we're talking about include thinking, acting together, making commitments, coming up with a purpose, feedback, learning, and so on. I encourage you to have a look at this idea of design from the cybernetics point of view. And I invite you to think about Jupyter not as a tool that is just for computing, but a tool that is an interface to have conversations, a shared language, if you will, to increase agreement and to lead to trust, because reproducibility is really about trust. Now, I don't expect that we are going to solve reproducibility with any approach that takes away the responsibility of the human participants, that attempts to work with one click. I have seen several tools have been proposed that attempt to solve the problem of reproducibility with just one click, and that is not a conversation. I have a button here, I press the button. That's not a conversation. We cannot relinquish the responsibility of the human in the loop for reproducible research, which is essentially about trust. So that's my message today. Reproducibility is not a one-click solution, and we can seek inspiration in several sources about design to think about how to accomplish the goals of Claerbout's group of achieving fully complete reproducible computations. Thank you.